Okay, so a very warm welcome everyone to this session of our Portal Seminar Series. Today we have Valia Allori from Northern Illinois University, and her talk will be what is like to be a GRW theory. So thank you very much for having accepted the invitation. I'll leave it to you.
Okay, so yeah, no, thank you for inviting me and having me present this talk. So so I couldn't resist making a joke, actually with two jokes and making fun of two important papers in the philosophy. So if you recognize them, good for you. Otherwise, go read them. Anyway, just kidding. All right. Okay, so here is an outline of the talk, and actually I should put my my timer on so that I don't go too much overboard. So this talk will be about the claim, the evaluation of the claim that theories like some spontaneous localization or spontaneous collapse are a better option as a quantum theory is compatible with relativity. So I will review kind of briefly first what is the problem with quantum mechanics, what the solutions are very quickly, where the claim that spontaneous collapse theories are to be favored among the various theories of quantum mechanics because of their compatible with relativity. I'll talk about Bell's theorem and Bell's violation, the violation of Bell's inequality, and talk about what the claim actually can mean. What does compatibility with relativity mean? What are the options, and how different approaches get closer to such a compatibility, and then at the end make an assessment. Okay, yes, as you all know, the trouble with quantum mechanics is this is what people usually say, that the problem of quantum mechanics is. I think that there is another problem, but it's not going to be relevant for this talk, at least. So the problem of the Schrödinger cat, or the measurement problem, is usually stated as this an incompatibility claim, like if the wave function is complete, provides a complete description of a system, and it evolves according to the Schrödinger equation, namely, which is in a linear equation, then there are superpositions at all scales. However, this predicted macroscopic superposition are never observed when we the famous experiment when we open the box and we find the cat either dead or alive. So there's a sense in which the theory is kind of empirically adequate as stated. So we need to fix it. Of course, this was known to everybody. And so usually this was fixed. This is fixed in the standard quantum theory using the collapse rule, but the collapse rule, it is unclear when to apply it because it has to do with measurement. So what is the measurement? Why a measurement is not just like another physical process? What is an observer performing the measurement? Do we have to invoke consciousness? So if we want to avoid all this kind of situation, then in order to avoid this kind of problems, people developed what we can call more precise solution of the Schrödinger cat problem, like the tidal wave theory, which is also called Bohmian mechanics, or the Broglie-Bohm theory. I mean, all these theories have different names, so you call them as you like, as long as we understand each other. This is a theory in which the state is given by particles, and the wave function needs to be, the information contained in the wave function needs to be provided in order to complete the dynamics. Namely, you have the particles, they move around according to an evolution equation governed by the wave function. Then we have the spontaneous localization theory, also known as spontaneous collapse theory, also known as dynamic reduction theory, or GRW theory, from the names of the proponents of one of the first very working theory like that. This goes. So the idea behind this theory is to say, look, the unitary evolution, the Schrödinger evolution doesn't hold any longer. What happens is that the fundamental equation of motion is not deterministic. It's not even linear. It is non-linear and stochastic. According to some people, including the GRW, this theory is not really a theory about the wave function alone, but you need actually something to connect this theory to space-time, and that's where the need for what is usually called primitive ontology comes in. But the basic idea, forgetting about terminology, is that the wave function being in configuration space doesn't really is not really able to account for the behavior of matter. You need something in space-time, and that space-time entity is what represents matter in the theory. So people usually people who believe that this primitive ontology is needed, including myself, talk about the GRW theory, specifying what kind of ontology of matter they have, like matter ontology, discrete spatial-temporal ontology, or particle ontology. Then there is another one, which is the many-word theory, or the Valia mechanics, in which the idea is to keep the unitary evolution for the wave function and allow for superposition to be actual. And that develops, and that gives rise to the idea, gives rise to an infinity of words which are actually, actualized. And so people need to account for why it seems like we live in only one. So this idea would require a completely different talk. I will not mention many words further in the talk. I focus on the comparison between the pilot wave theory and the GRW theory, especially in light of the claim that some people have made that GRW theory is more compatible with relativity than the DBB theory. Okay. So what is the idea? What is the tension that we are talking about? So I mean, okay, so we had quantum theory. Quantum theory as it has the measurement problem. The measurement problem can be fixed with this precise solution, but still, right, we also have this other theory, the relativity theory. What do we do with that? How can we put these theories together? So there is a tension between these two theories, which is given by the violation of Bell's inequality. So what I'm going to do is kind of quickly overview what the problem is supposed to be. So I'm just going to quickly talk about the EPR part, the EPR experiment, thought experiment, how that was taken up by Bell, see how the inequality came about, and what the experiment said. So EPR, Einstein, Podolsky, and Rosen wanted to show that quantum mechanics is incomplete. Otherwise, they would there would be non-local correlations. Okay, so and they thought, so I mean, the idea was that their starting point was, and here I'm following several scholars. I know there is a huge debate on that, but I mean, I'm just following the debate of those, there I've studied Bell and like Norsen, Brickman, and Maudlin closer than others. So the idea is that Einstein, Podolsky, Rosen thought that non-locality was something which was unacceptable. And this boils down to the idea that of locality in itself. Locality is the idea that systems influence one another, and this influence is traveling through space-time, right? And is not instantaneous. This is a very long story. This is something that people complain about Newton's to start with. And arguably, Einstein, Podolsky, and Rosen were thinking, especially Einstein, you can read this sometimes in what he writes, you can extract it, that if if influence were instantaneous, then it would be impossible to think of system as isolated, right? So the idea is that, I mean, how can you if you had, no local correlation, systems interacting with one another instantaneously, independently of their distance, how can you possibly identify this system as distinct to this other system? How can you possibly identify this event being a cause of this other event? So that was the original worry. In addition, so it's not necessarily a problem with relativity in itself. It's more like concerning a problem for, a kind of theory that you would like to have. Relativity then poses this additional constraint that, light travels. Nothing can travel faster than light, so including influence. Right. So here's very quickly, hopefully not too overwhelmingly, how people how EPR arrived to their incompleteness conclusion. So this is actually the formulation that was later put forward by Bohm and Bell. They assume locality for the reasons that we saw. They took standard quantum mechanics to be true. And so the thought experiment was supposed to go like this. You have a pair of entangled particles in spin emitted in opposite directions. Neither of these particles has spin's properties according to standard quantum mechanics. So if you take the singlet pair, okay, you can talk about the property of the pair, but not a property of the components. So, and then you have this famous Alice and Bob on different sides. They each make a spin measurement along one direction, a given direction, and their results, they compare their results, and what happens is that their results are perfectly anti-correlated. So everyone, every time one measure spins up, the other measure spins down. And so, so the idea is that, each particle has to acquire, they concluded, a spin property upon measurement, right? And because of the collapse rule, right? The collapse rule is instantaneous, but in virtue of this, is also non-local. And they said, this is impossible for the reasons that we have talked about. So we need to explain things differently. So how do we explain this differently? Well, the system, right? The two particles show correlation at the outcome because they were correlated all the time. So this is, the idea. You have two balls, one pink ball, another ball. You put them in boxes. You prepare many pairs of boxes. For each pair, you send one in Chicago and the other one in Milano. You keep repeating this for each pair. Every time Alice in Milano opens the box and finds the pink ball, Bob in Chicago finds a yellow ball. So they're perfectly correlated, but that's no problem. That's not surprising. What's the point, right? The point is that they were colored all along. And when Alice opens the box, her color measurement reveals the color property of the ball. There is no local action at the distance, of course, right? Correlation in the outcomes is explained by correlation at the source. So the idea is that the very same thing is true for spin. This is exactly the same. I'm not going to read it. It's just like the very same slide as before, but with spin instead of color. And so this is what they concluded. EPR concluded that particles have spin properties all along, and when Alice measured her particle, her measurement reveals the property that her particle had. So EPR said, look, the non-locality that you find in standard quantum mechanics is just artificial, right? It's not that, it's weird, or there is some kind of very strange thing going on. You can account for these findings, like the perfect anti-correlations, not postulating this weird no-local action at the distance, but simply saying, look, the description that you're providing, standard quantum theory, is incomplete, right? You need to specify what the spin properties have been all along, right? So the idea, they took this no-locality as an evidence of incompleteness. Okay, so to make a point, to continue with this, right? Bell came and said, okay, right, standard quantum mechanics needs to be completed in order to explain the correlation locally. So Bell said, this is what EPR wanted to show. And now he asked, look, would such a completion of standard quantum mechanics makes the same prediction as quantum mechanics, or it would be empirically distinguishable? And it turned out that if it's same as Bell's inequality, the answer is actually negative, right? If you complete quantum mechanics as EPR wanted, right, namely adding these quote hidden variables in which this hidden variable are the preexistence property of the particles, like the spin properties, then it would make different predictions. So he set up an inequality and said, okay, right, you can go out. So if quantum mechanics is true, then it violates the inequality. Otherwise, it would not. And the picture over here is Alain aspect. And so the experimental, that this can be experimentally checked, right? And in the word of aspect, what this is supposed to establish, right, is that, his experiment showed that no locality is the real deal, right? So the perfect correlation observed in the experiment cannot be explained as EPR wanted. And so all quantum theories have to be non-local. So this is an actual blow. Okay, and some people usually say nature is no local. Oh, come on, that's exactly, that's a, extremely, extremely, extremely surprising, extremely, difficult to swallow. Because of this, I mean, partly because, for the reasons that we already said, right? And, how can we possibly then talk in terms of influence which travels at finite velocity? This is not the case. And because of this, many people have tried to reject one assumption or the other of Bell's theorem. Some people, I mean, included into the derivation, something which I haven't mentioned in the derivation, which I didn't present, is this hypothesis of statistical independence. There are certain theories that are called superdeterministic theories, which reject that, which means allowing experimental outcome to be determined by what the experimenter decide to measure rather than the actual value of the property being measured. Bell was questioned about this, and he didn't think that the theories are even viable. Retrocausal theory allow for events to have causes in the future rather than in the past. So we're not going to talk about, I'm not going to talk about these things at all. I assume, okay, that the violation of Bell's inequality establishes no locality, because it's interesting to notice that there are some people, including Bell, first of all, and then Tumulka, and then Girardi, and then Wayne, that have said at certain point in their papers that GRW or somehow spontaneous, some version of relativistic spontaneous collapse theories should be preferred to pilot wave theories, because even if they're both non-local, the former is somehow more compatible with the spirit of relativity. So I think this is a very, very interesting claim that needs to be explored. This is the main reason why I got interested in a little bit more in GRW theory, to try to explore what to make of that, right? To try and figure out whether, which kind of approach, which kind of research program should we pursue, and in what respect, what kind of consideration should we use to implement it. So in order to evaluate the claim, right, is that the case that GRW theory is more compatible with relativity than DBB, we need to better understand what is the nature of the tension and what is the spirit of relativity. Sometimes people, they say, oh, the spirit of relativity, but what do they mean, right? We know, I mean, sometimes people talk about relativistic invariance, right, Lorentz invariance. So what is the connection with all these things? So this is what I'm trying to do in this talk, in the rest of this talk. Right. So here's a bunch of things that people agree upon, right? That, standard quantum mechanics and theory and relativity theory are in tension in the following respects, right? The so-called dispersion relation, the relation between the energy and the momentum in the Schrödinger equation is not relativistic. This can be taken care of implementing a different kind of evolution equation with the correct dispersion relation, like a Dirac on a Klein-Gordon equation. The second obstacle is the wave function in itself is a function of a single time. And, and that means the wave function is this object, which is in configuration space, namely the space of configuration, the space of the configuration of all particles. So it's a and it's a single time, right? And so in order to say, oh, so this is suggesting the idea that there is some notion of absolute simultaneity. So how can we, and we know that the notion of absolute simultaneity doesn't sit well with relativity. So arguably there's also a way to fix that. And some people have proposed to reformulate relativistic version of these theories in terms of what is called the multi-time formalism, in which different system evolve with a different time parameter, so that they can evolve independently in a sense. And then of course the third problem is that there is the collapse of the wave function, at least in GRW theory, or more in general, which is non-local, or more in general, interaction in itself is non-local in theories in which the wave function doesn't really collapse, like for instance, like the pilot wave theory. And for this, there is no real fix. The non-locality of nature is something that I'm granting the EPR and Bellin aspect have proven. So granting this, right, what are the other considerations that make people, including myself, my past self, say, oh, the GRW theory is better suited to as a model, right, as a preliminary version of a more general theory combining relativity and quantum theory. Okay, so let me do a very quick review of the main ingredients that the various theories and on one side pilot wave theory, on the other side the GRW-type theory. So there are versions of relativistic theories in both camps, right? See what are the main features. Okay, so pilot wave theories have been proposed to be, people have proposed different relativistic extensions of those. You can guarantee the Lorentz invariance, connected to the having the correct dispersion relation, providing an evolution, a Dirac or Klein-Gordon equation for evolution for the wave function. These theories are explicit, non-local, in the sense that the interaction is mediated by the wave function, and the wave function is a function of the particle configuration at the same time. This again suggests the notion of absolute simultaneity, and again this suggests the existence of a global spatial temporal structure. So what do we do with that? Well, one obvious possibility is to postulate this preferred foliation of space-time in which the interaction happens. All right, so problems with that, people complain about it, and the fact that it's unobservable. And this concern is kind of motivated by the idea that what is unobservable can be eliminated. Okay, the idea is, look what happened in Newton, right? Galilean space-time arguably come from the observation that absolute velocity are not detectable. As a reply, one can just say that, well, many things which are importantly, they're explanatory are unobservable. So the claim that what is unobservable can be eliminated is too strong. I mean, as an example, Newton was just, as we're saying, absolute acceleration is not observable, but still, it's needed to explain certain features. In addition, one can also argue that there is an explanation of why the preferred foliation exists, right? And it's It's unobservable, right? This is connected to the fact that we don't have access to the position of particles with absolute precision. If we did, then we could have access to the foliation. So it's not like completely, it's not arbitrary at all. There is an explanation. It's not arbitrary that it is unobservable. You're not saying, oh, it's unobservable because I need it to be unobservable. No, it's unobservable because of something else, namely quantum equilibrium. Some other people have objected that it's artificial, right? In a sense, right? Oh, you have to somehow, you want to make the theory relativistic, compatible with relativity. So, and that's what you do. You need the foliation, you just put it on. And that's kind of, and that's kind of, ad hoc, does not arise naturally from the theory. People in the literature have replied with a different proposal in which they say that, in which they actually put forward this preferred foliation of space-time as extracted from the wave function. So their claim is that, and I'm not making any references because there are many authors, so, but if you need references, I'm just gonna read them to you at the end and direct you to papers to read. But the point is that, there is the wave function. As long as you have the wave function, right, you can extract the wave function from that with a given function. And this is supposed to be, what the authors say is that it's not only, it's in virtue of this extraction from the wave function, right, that all quantum theories in virtue of having the wave function also have a foliation too. Well, personally, I'm not particularly convinced about this argument because, simply because you just have a mathematical object that can be extracted from the wave function doesn't mean that that particular mathematical object has physical significance. But, this is what they say. Okay, so bottom line, it is the same slide as before, except for the last 3 lines. These proposals are relativistic. In what sense? Well, in the sense that they had the right, dispersion relation, they are Lorentz invariant, including the foliation, but the interaction, okay, is non-local, which is unavoidable given Bell. And, they have this non-relativistic spatio-temporal structure, which is added, right? This global structure, which is added. Okay. What about relativistic GRW theory? Okay, so there is a long story about proposals that are successful, that they failed. I'm just, cutting out a lot of details. Those which seem to be more promising are listed in the end, but let me just, talk about the main features. Okay, they are non-local, right? For anything, just because the collapse is built in the wave function evolution. They're Lorentz invariant, however, because there are evolution equation and which are suitably connected to Dirac and Klein-Gordon evolution. Use the multi-time wave function formalism. What Bell noted was Bell was the first who actually said, look, there is something interesting about the GRW theory. He was focusing on this particular version, which is called GRWF, in which the wave, the basic picture of the world is not given by the wave function, but the collapses of the wave function. This provide the collapse location and timing, right? They form a collection of what is called flashes, events in space-time, right? And the idea of this GRWF theory, GRW flashy theory, is that matter is made by a collection of these flashes. And Bell observed that these flashes, right, as an important, this GRWF has the important feature of being relative time translation invariance, right? So to distance system can get shifted, right, in time by different amounts. And he said, look, this is interesting because it is And it can be seen as the kind of a non-relativistic shadow of Lorentz invariance, right? Because it is equivalent, assuming that simultaneity in absolute sense play no role in the theory. Otherwise, the two times in the two different systems could not be shifted independently. So taking advantage of this observation, Roderick Tumulka in 2006 proposed this relativistic version of the GRW theory using no preferred foliation. He was using an hyperboloid, he could define the law of evolution for the flashing without adding anything at all to the structure of space-time, taking advantage of the particular ontology. Later on, in 2014, people also developed a relativistic version of the GRW theory, in which instead of having flashes, we have a matter density field. So the matter density field in three-dimensional space is supposed to be, coming from suitably projecting the wave function in configuration space into the three-dimensional space. And this one was originally proposed by Gherardi, which was one of the co-author of this 2014 paper. So aside from the details, what's going on in this theory that, again, right, they're Lorentz invariant, right? They are non-local unavoidably, but what seems to be extremely promising of this is that there is no non-relativistic spatial-temporal structure. In the case of the relativistic GRW theory, they're using the Lycon structure to define properly the matter density field. Okay. So here's the comparison, right? So the summary of the previous slides, relativistic pilot wave theories are such that they're Lorentz invariant, they're non-local in interaction. They have this, however, global non-relativistic spatial temporal structure. Instead, the relativistic GRW theory are Lorentz invariant, so check, check. They're non-local, check, check, but they only use relativistic spatial temporal structure. So it is in the virtue of this last bit that many have argued that relativistic GRW theory are more compatible with the spirit of relativity than relativistic pilot wave theories, right? So I'm just going to criticize the last claim. I mean, I'm actually not sure if I'm criticizing. I mean, yeah. So I am criticizing it, but you can take, at least, even if you don't disagree with my conclusion at the end, right? Hopefully, what I'm going to do is going to be helpful in trying to see what the cost and benefits are of both proposals. Okay, so what do we mean by the spirit of relativity? Okay, so there seem to be several possibilities. I mean, talking to people especially. So one possibility straightforwardly is something like this, right? Relativity is fundamentally a theory about space-time, right? It's a theory about about that. As a consequence, right, theories would have no spatial-temporal ontology, like in the case of wave function realism, in which everything is just like in configuration space, violate this spirit, arguably. But so we can just say, okay, right, relativistic GRW and pilot wave theories, assuming that we can, take them as theories in which the wave function does not represent matter, but codifies something about the interaction, then these theories do not have this problem. So they are, in line with this spirit. Another possibility is just to say, no, it's not about space-time like that. It has to do with the spatial-temporal structure. Right? So they're not requiring the matter to be in space-time like the first spirit suggests. Rather, you're actually talking about, the structure that you need to postulate in the theory, and that is need to be compatible with relativity, right? So if that's the case, then of course the global spatial-temporal structure postulated by relativistic pilot wave theories is violating the spirit, and GRW theories, relativistic GRW theories do not. Okay, just like, of course, right, the last spirit, right, the one that arguably EPR wanted, namely locality, fails, right? No theory can respect this theory. But, you know, the reason why I mentioned this is that an observation is that pilot wave theory are, in a sense, as local as possible, or better, the least non-local, while that's not the case for relativistic GRW theory, which are non-local even when it's not needed. So I will try to clarify what I mean by that. Okay, so one could, I mean, just like to try and understand better what's going on. So one could in principle have the following, to think that there are the following possibility in mind: a theory with local interaction and exclusively relativistic spatial-temporal structure, a theory with local interaction and non-relativistic spatial-temporal structure. Actually, 1 and 2 are not a possibility because of no locality is true. So 3 and 4 are the only options, right? Non-local interaction, one exclusively relativistic spatial-temporal structure, and the other one a non-relativistic spatial-temporal structure. What I'm going to argue instead is that that's what people usually think are the alternatives, but no, what I'm going to argue instead is the alternatives are not between 3 and 4, but between 4 and 5 and 6. One theory which is super non-local and only a relativistic spatial-temporal structure, and the other are merely non-local and, you know, having just non-relativistic spatial-temporal structure. Okay. So very quickly, let me ask, okay, so one important question that needs to be addressed is what is it about the GRW type theory that required no foliation whatsoever? When we think, okay, it's about the multi-time formalism, not really, because I mean, people have explored the issue and some relativistic pilot wave theories use this kind of formalism. Is it about the flashy ontology? No, because, or the particular type of ontology, is something wrong with the particular ontology? What's going on? No, actually, because I mean, as we saw in 2014, relativistic GRW R theory has been proposed, and arguably there is a possibility of doing a very similar strategy for GRW with particles. Is it about the type of spatial-temporal structures? No, because one uses the hyperboloids and the other uses past coins, so it's not really that. So what is that? I mean, and this is coming from, you know, not only my observation, but this has been observed by many people, including Wayne in his own papers. It has to do with the stochasticity of the interaction. So there is a sense in which RGRWM and RGRWF are doubly stochastic, in the sense that, you know, the interaction, the evolution equation for both the wave function and matter are stochastic. There are proposals of doubly deterministic theories, in which, you know, like the pilot wave theory. There are proposals of deterministic wave function and stochastic matter evolution, but they also require foliation. So people have tried to wonder and say, look, right, but can we actually have a deterministic foliation free theory, right? That would be nice. Arguably, the answer is negative, right? So this is a kind of a theorem that Ghirardi and Grassi have proven in 1996, and that proves to be correct, that only stochastic theory in the evolution of a wave function can be foliation free. So it is in virtue of the stochasticity of the law that relativistic GRW theories are foliation free. Okay, so this seems to be the situation: stochastic foliation free theory and deterministic theories which are non-relativistic space-time structure. Okay. So what's going on? All right, so we have this. So is it really true that we should prefer the stochastic theories Okay, so here are, I mean, the next few slides, I'm just going to talk about what the consequences are of this theory. So first, I'm just going to talk about the ontology they have, the type of law they have, and the consequences for more macroscopic concept like cause and effect. And in the end, I'm just going to talk about the notion of interaction. So in virtue of these consequences, I think it's kind of premature to claim that GRW-type theory should be preferred to pilot wave theories in the extension to this theory to relativity. Okay, so unfamiliar ontology, unless we have an RGRW-P theory, the theory of particles, right? We're stuck with an ontology either with a matter density field or a fleshy word. Okay, and the matter density field, right, which is defined in terms of the wave function, it has the tail of the wave function itself, and that has been noted by Peter Lewis, especially that macroscopic solid objects have tails, which other object could cross without being subject to any actual interaction, and this is very different from what we could expect. In the case of the fleshy theory, this is extremely discrete ontology. Material objects are made up of spatiotemporal events and therefore are mostly empty, both in space, like in the atomic picture, but also in time, right? They go in and out of existence. And so the flesh ontology clashes with our intuitive idea that macroscopic or even mesoscopic objects, for instance, like molecules, exist continuously. Okay. What about the stochasticity of the laws? Now we're comparing the alternatives. It's just like stochastic law against deterministic laws. They are not as simple. I mean, people have objected to that kind of laws for a variety of reasons. In particular, in the case of GRW, they also seem extremely ad hoc. You know, the parameters inserted in the laws are, you know, ad hoc, postulated in order to avoid falsification. But I mean, this is not necessarily an objection to the stochasticity, it's just an objection to the law themselves. In general, talking about stochastic laws, it's less clear what kind of explanation they provide. In a sense, the principle of uniformity of causation that, you know, the same cause will have the same effect doesn't hold. Can we make sense of the notion of probabilistic causality? Can we talk about propensity? Do we have to talk about disposition? So it opens up, you know, to many open questions. I mean, just like, so the point being, right, if there were no alternatives, right, we have to accept what we have to accept, but we do have alternative deterministic laws, so it's kind of difficult to somehow justify this without any other reason. And I mean, and this is recognized by many working on this. So I'm pointing that out, right, to everybody. There is just more than just the failure of the principle of uniformity of causation. There is symmetry between cause and effect, right? There are no continuous word lines. Matter with two T's jumps around. And this, you know, suggests, right? I mean, it has been recognized. You can read it, you know, even by the proponents of this theory, like, for example, Radi Tumulka. It says, well, there is no cause and effect. Cause and effect vanish, right? No event can be considered the cause of another event in absolute terms. And so one can just say, yes, so what? Well, what? In the sense that, I mean, this just seems to be threatening the notion of influence in itself. Why? Well, how can we make sense of the notion of influence, right? So the notion of influence is just like this guy over here is interacting with this other guy in the sense that the presence of this guy influences the presence of this other guy. So, but if there is no cause and effect, right, the influence doesn't travel. How can we, I mean, if there are no cause and effect, how can we possibly make sense of the notion of interaction, of influence? Okay, so in addition to that, as noted by Jean Brickman in particular, also other commentators notice it, but I mean, he is the only one that I've seen that is just like taking that to be extremely a problem for this theory. This theory are, and this is the way in which I call them, they're super nonlocal. They display no locality only for one particle. So this can be seen with a simple example. So suppose take, for instance, GRWM. and take a particle confined into a box. Then you put a barrier into the box, right, and create two boxes. You separate them out, right? Given that there is only one particle, no collapse that actually happened, and matter density is half in each box, right? They're separated. Now you open one box, the particle gets coupled with the measurement device, and the wave function most likely collapses. So the matter density all jumps in one of the boxes. And so you have no local transfer of matter even with one particle. With one particle, you have no local interaction. How can that make any sense? All right, so what can you say? Well, no, there is no matter, no transfer of matter involved. It's just like shining a laser pointer across the face of the moon. The spot can move faster than light, but the spot is not really a thing that moves. Actually, no, because this option, right, cannot really be what's going on, right? The spot, I mean, the matter density is what matter is, so you can't really say something like that. Some other people have objected to this by saying, well, who cares about superno locality, right? Locality, no locality, no superno locality, well, whatever, right? It's not, both theories are no local, right? The fact that one is superno local, yeah, whatever, right? It doesn't really matter, right? How many times a principle is violated. It's violated, period. However, the important thing to notice is that this superno locality is not necessary. Namely, there are other theories in which they're only local, like the pilot wave theory. And in addition, right, you think about what, so superno locality is no locality with one particle. So you have no locality with no interaction. So the idea is that locality is a feature of composite system, right? You have two things and they interact with one another, either locally or non-locally. In here, you have one thing and it's non-local. Yeah, so it's unclear. So it seems like if the example before was threatening the notion of influence, this is just like, yeah, the notion of locality seems to be, quote, meaningless. So it seems to me that, you know, if the original motivation for having a relativistic GRW type theory was just like they make it more like, you know, peaceful coexistence with relativity than other theory, right? They do respect one spirit very well, right? In the sense that no relativistic spatial temporal structure. It's true, that is certainly true, right? But they completely lose the other spirit of the locality of interaction or the idea of interaction in itself. So, and I do think this is my last slide, right? Almost, yeah. So what does it mean that non-local quantum theories are relativistic, right? Because that's what they are. Well, if it means, I mean, it could mean the locality of interaction or that they respect the relativistic spatial temporal structure. Relativistic pilot wave theories violate the spatial temporal structure, but they are the least non-local. Relativistic GRW theory respect the spatial temporal structure, but they are super non-local. So relativistic pilot wave theory, they do have also a simpler ontology, a nicer deterministic evolution, and a nicer explanatory schema, right? Particles, you know, making, you know, making stuff up in terms of Lego bricks. Instead, you know, the relativistic GRW theory, yeah, they respect the spirit of spatial temporal spirit. They're super non-local. They have this unfamiliar ontology. They had this ad hoc stochastic laws that makes them unclear in what sense they are explanatory of the macroscopic phenomena, because especially there is no cause and effect. And there's, I mean, in what sense stuff is interacting with one another, given their super non-locality. So when we're talking about, so my point again is, sure, right? I agree. I mean, we started off with saying, look, you know, I mean, we started off, I mean, it's, I agree with the conclusion, with the claim that relativistic GRW theories respect the spirit of relativity in the spatio-temporal structure, but as a consequence, they are super nonlocal, and as a consequence of that, they also have, you know, it's totally unclear what the notion of interaction may mean in these theories, and this again would threaten the idea that these theories are explanatorily superior than these other theories, than the, you know, the relativistic pilot wave theories. Right. So thank you for your attention. And thank you so much for bearing this with me. Okay, and here you are.
Thank you very much for your talk. So we have now the Q&A.
Yeah.
Okay, so Wayne first.
Thank you very much for this, Valia. We should sit down and talk at length about this. You raise a lot of really interesting points, and as you know, this is stuff I work about on this. So yeah. I'm going to confine myself to one thing. You're focusing on relativistic versions of GRW theories, but there's a number of arguments in the literature, like that a really relativistic quantum theory should be a quantum field theory, not a theory of finite number of particles. And so for that reason, people have thought that the CSL theory would be a more promising place for relativistic quantum theories. And there are relativistic versions of the CSL theory that developed by Dan Benningham and Philip Pearl. And related to that, I think is this issue of super non-locality. It seems strange. It seems strange that there's non-locality when there's only one particle, but once I start talking about quantum field theories, interaction field theories, then number of particles doesn't really make sense. But also, okay, if you're worried about super non-locality with only one particles, it's even worse, because in a quantum field theory vacuum, there are Bell inequality violating correlations between space-like separated regions, and I think any theory that that accommodates that is going to be super non-local. You're gonna have non-locality with no particles, so which makes me less worried about with one. And you think, so how do we make sense of locality of interaction? I think when you're talking about a stochastic theory that has stochastic law of evolution, it's especially one like this, which has space correlations between events with space-like separation. I think interaction isn't the right word, but for the relations between these space-like separated things. You've got there's something very non-local about the evolution, but in the stochastic theory, it's not clear that interaction is the right word. Non-local interaction is the right word. And then the worry is, does this make sense? It makes no sense to talk about interactions. Well, in a theory like that, it's still, if I model, you still say, okay, I pick up this coffee cup and I raise it and I'm interacting with that. That's fine. It's not. I don't think there's a worry that the whole notion of interaction goes away, even though you're not going to be able to apply it to where in cases where you might think you would be able to apply it. So, I have a series of comments rather than questions. I'm sorry, but
no, I mean, absolutely, yes. Okay, so let me see. All right. So about the first thing that you mentioned, what about fields? So I don't know why people claim that you have to go that way. I mean, after all, there seem to be extensions of you know, sufficiently relativistic theories without the ontology of fields. So unless I see a very strong reason to believe that we have to have fields, I would worry about that. But I do think instead that yeah, so the true thing, the true question over here has to do with you know, what to do with this business about Superno locality and having the notion of interaction, having to abandon the notion of interaction. So yeah, so as I was trying to say at some point, you know, I got really interested in GRW theory because of this lack of you know, the lack of, you know, surplus spatiotemporal structure. But then if the cost of that is to abandon, you know, the notion of interaction, abandon cause and effect, abandon all these things, then you just say, okay, right, maybe I do want to go that way. But I mean, this, so I want to abandon the notion of interaction, and I have to have it in order, I can do this only with stochastic theories. And so, I mean, forgetting about the unfamiliarity of the ontology, maybe you can do with the particle ontology, but I mean, the cost is this. Okay, no spatiotemporal structure, which is not relativistic, and then you have stochastic theories in which the notion of interaction loses its mind. So I do have this, and on the other side, I do have, yeah, you have, you know, this preferred foliation, but then the notion of interaction makes sense. If you just have these two things, which one are you going to pick? Well, I would pick the one in which the notion of interaction makes sense, right? Also because we have reason. So because, I mean, insisting on the other stochastic non-interaction sense, you know, this is, in what sense it's more incompatible with relativity? I mean, Einstein liked relativity because, you know, it made sense in his mind. He wanted to have interaction. He wanted to have locality. So we already know that locality is not possible, right? So is there a way in which to keep the notion of interaction? So maybe relativity is mistaken also in the sense that maybe it does have a spatiotemporal structure, right? So, I mean, these are options to consider, you know,
let's talk more, because as I said, I don't think in a stochastic theory you are abandoning the notion of interaction.
Yeah, okay.
So it's not as dire as it might seem.
No, you're right. I mean, I don't. Yeah, I mean, yes. Yeah, let me just like rephrase, because I actually didn't mean it to be so strong. So it seems like the notion of interaction seems to be abandoned. So my point is going to be, if you have to pick between the theories in which you have a preferred foliation, the notion of interaction that makes sense for sure, and the theories in which no preferred foliation, no foliation free theories, in which the notion of interaction need to be recovered in another way, which isn't obvious, then, you know, it's unclear to me that we should go for the latter.
Okay.
Yes.
Okay. Yeah. So let's talk more at length, because I think I can sit down and tell you what the notion of interaction is in these things. It's actually
that's great. Yeah.
And there are more hands, and I don't want to take more time.
Okay, so Carl Hofer.
Hi, nice to see you again, Valia. I just wanted to ask about your single particle super non-locality objection, because it just seemed to me that it's not right to say it's a scenario where you've just got one particle, because you've got whatever is making your boxes. I mean, whatever is doing the job of dividing space and then separating and all that. And if it was real boxes, it would be 10 to the 23rd particles. If it was something idealized, some high potential barrier that you're talking about, doesn't matter. There has to be something else in the universe, and that thing is explicitly interacting with the particle, and that's why you get this this behavior that you were talking about.
Yeah, so I mean, the example is not mine, it's taken from Jean Brickman, and I'm using it because I think there is something to it. But I think this should be understood. I mean, this is something that happens with any type of GRW theory, right? In which, so your point is that, well, the way, when we're preparing the thing in the box, it's not really one particle. But I do think that you can prepare it that way. You can just somehow, this preparation procedure will ensure, right? So there are ways in which you can just say, okay, this is the equivalent of, right, what we would normally treat as a one particle system, right? So this, the preparation procedure leads you to this box, which behaves as if there were another, a particle, right? And then starting from that, you take the box and you start dividing it, right? And then you do have this, which is odd, right?
It just seems to me that what you're doing is, I agree that you're forcing a single particle to do something that looks non-local. It's just that it's not as dramatic sounding as if the particle was sitting all alone in the universe and then splitting itself, and then spontaneously collapsing.
Right. Okay. Yeah. So, I mean, let me also add this other thing, right? So people do not really talk about this as much because there is little reason to. I mean, but it is, you know, you can construct a GRW theory with particles, right? Which, I mean, they do horrible things like, you know, they jumbled around again, right? But I mean, instead of having the mass density or the flashes, right? These are just like discontinuous particle trajectories, right? And in that case, right, it would be undeniable that there's just one particle in that way. Right. So what you can say, okay, right, this is more reason to say, okay, this theory is just like not to be taken seriously, right? Yeah. Okay. Yeah, I just wanted to make the point. So, but I do understand, right, that in the case of the matter density, right, it is less dramatic as with the particle case with the ontology of particles. Thank you.
Okay, so Alvaro.
Yeah, hi. I wanted to clarify on the same example. Does the fact that you're dealing with relativistic theories make a difference with a non-relativistic GRW theory? Because in a GRW theory, you will also have some sort of collapse, and this will be non-local. So my question is whether this theory being relativistic in some sense makes this super non-locality appears, or
No, it's just this theory is just like, I mean, GRW regular is super.
You will have this.
Yeah, I mean, Jean's example is about the regular GRW theory.
Okay,
So yeah, that, I mean, the thing is not going to improve in any way. If it is a problem, it's a problem all over.
Okay, thank you.
Oh, thank you.
Okay, so Bigmund.
Hello everybody. Yes, I mean, I can answer Carl's objection. You can think of, instead of having a box cut into two, you can just think of one particle in one dimension and the wave function spreading in two different directions. And then when you measure at one point, then you know, in the GRW theory, I mean, it's half of matter density and then a matter density jump, because you never see half a particle. So the matter density jumps from one place to the other. And that's a non-local transfer of matter, which is very non-local and not necessary. The other thing is I wanted to ask, I think I've already asked you and I never understand the answer, is you see, if you take this business about Alice and Bob, and they have the entangled pairs of particles, and we are in the laboratory and we speak in the frame of the laboratory. Now, Alice can, let's say, measure the spin of the particle first, before Bob. I have to start with Alice, of course. And she collapses the wave function of both. And then Bob's particle spin is fixed, right? And that's a non-locality in ordinary quantum mechanics. Now, Einstein thought you could restore locality with hidden variable, and we know that doesn't work, but you know, okay. But to me, it seems perfectly clear what is the cause and what is the effect. If Bob was measuring first, he would collapse the wave function on both sides, and then Alice would be fixed, right? So how, I mean, how do you do in GRW to eliminate the notion of cause and effect? That's my first question. The second question is, if you are willing to eliminate the notion of cause and effect, then why can't you just do the Breuil-Bohm theory or guiding wave theory in a block universe? In a block universe, as far as I understand, there is no cause and effect. But I don't know if you would say that there is extra spatiotemporal. So, I mean, why wouldn't that be perfectly compatible with relativity if you give up the notion of cause and effect? You see, because the whole, I mean, somehow the whole problem, of course, came from the fact that we believe in cause and effect, maybe wrongly, so as Russell said, but we tend to believe in cause and effect. So if you give up that, why not do the block universe stuff and then do guiding wave theory?
Okay. All right. So the first question was in what sense GRW theory loses the notion of cause and effect?
Well, in the scenario that I gave you, which is very clear.
Yeah. And so the point is that in the scenario that you gave me, Alice measured first, and so causes okay, right. And so I mean the point is in which the GRW relativistic GRW theories would make, I mean, this would be clear in one frame, okay, but so it's relative to the frame, right? In absolute, there are no cause and effect, right? And this is part of what's going on in the case.
Since they're in the same laboratory, you say, I would say, once they're in the same laboratory, it seems to be clear that there is a cause and effect, you see, intuitively. I know the business about relativity, but I don't see why I should go in a spaceship to describe this thing in the laboratory. You know, one pushes the button first and the other does it later, and then pushing one button causes an effect on the other side.
Yeah, so I'm not really sure we actually are disagreeing around here. So the point is that, you know, I don't care much about cause and effect, you know, cause and effect, but I do care about stuff influencing one another. And so, I mean, you can just say, sure, I mean, there is a sense in which, you know, in the example that you gave me, you know, Alice is influencing what Bob does, but there is no absolute fact of the matter, right? Because if you change the situation to another frame in which Bob was first, you know, the situation would be the opposite. And so one can just say there is no absolute, so is this happening or is this happening in space-time? So, I mean, it's not necessarily the case that I take cause and effect to be fundamental. And this leads me to the second point about the block universe. Again, presumably what I find difficult to digest about the GRW after having thought about it more is that, you know, exactly what's going on is that the notion of influence over there, right, as your example of Superno locality seems to be showing, is that, you know, sometimes there is this behavior in which, you know, weird stuff happens even when you have one single system, right? And that's very strange. I don't care much about putting stuff in the block universe or not. I don't think it's going to change much about the situation. So yeah, probably haven't responded to your question anyway, but that was my best.
Okay, thank you.
Sure. Thank you.
Daniel?
Thank you, Valia, for this interesting talk. Okay, I'm going to go back to this issue of the quantum fields. You mentioned you noted that you know, Schrodinger's equation produces a dispersion relation that is not covariant, and of course we have to go to Dirac and Klein-Gordon equations, and those theories contain these negative energy solutions and sometimes negative norm solutions that make the whole probabilistic interpretation of quantum mechanics problematic. So those are the things that forces you to go into the quantum field theory. I mean, Dirac equation, for instance, is nice if you avoid interactions. Once you allow for interactions, I mean, let me go back to the interactions later. Once you allow for interactions, these negative energy solutions are going to appear, even if you started with only positive energy solutions, and you have to make sense of that. So to me, the idea that we have to go into a field theory, sorry, I'm, you know, come from a very physicist kind of for me, the idea that we have to go eventually to a quantum field theory kind of setting seems quite necessary, although I recognize the very serious problem of trying to give an ontology to such theory. But once we accept that we must go into that direction, to me, this idea of super non-locality and as when mentioned seems very iffy, right? I mean, I'd like to think of a block universe populated with the space-time geometry and fields, and in that sense, everything, on the one hand, everything is extended, everything is interacting. We decide to chop the world into pieces for the benefit of our of trying to make the job of describing it possible, but in the end, there is one world with these extended objects that are the quantum fields, and then everything is interacting. The idea of isolated objects is an extreme idealization. If nothing else, the geometry of the world here is affected or is conditional or is, I don't know what term you want to use, by the distribution of matter all over the universe, right? The constraint equations in our modern theories, both of relativity and gauge theories, are constraints about data on the initial on spatial hypersurfaces. So there you have, complete influence, very clear and transparent influences that are not between causally connected objects. Of course, we know we don't want this to allow us to send superluminal signals, but in a sense, our split between interacting and non-interacting entities is in my view misguided. So okay. I wonder what your reaction is to my reaction.
Okay. Okay, so the comment of fields. All right, so okay, so fine, maybe we do need, I'm not okay, so my point about going with the pilot wave theory was not necessarily connected to the fact that you have to have particles as an ontology. It was more like, you have a clear ontology, you know what you're talking about. This could be an ontology of fields. They can evolve according to a deterministic equation. What's the cost? Well, you have to add a foliation. Okay, fine, but at least they understand, the interaction and what's going on. You have this non-local interaction, which is a very big deal, but it's and so I would be happy. If that's what we are required to do, okay, fine, let's move to fields. What happens in the other side is, okay, so we do have a field ontology, we have the stochastic ontology, then we have, and so you say, yeah, that's right, and you have to give, in the moment in which you give up to the preferred foliation, then you have everything interacting with everything else, or interacting, in a sense, you have to abandon this. Yes, I think, okay, that's exactly what the cost is. If you go that way, I'm not saying that you shouldn't pursue it. I do think that that's a valuable research program, and I wanted to see for myself. I need to think this through for myself. I'm very simple-minded. And I arrived to discuss and say, I like GRW. Why do I like GRW? Oh, because of this. No global structure, right? But then it is the cost. The cost is to really give up to the interaction. I didn't understand that before, and now I do. And so I thought, now you have to. I'm saying it to everybody. And so these are the alternatives, right? So if you want to keep the notion of interaction making sense, the ontology, to me, as long as the ontology is in space-time, I don't care what it is, fields, particle, whatever, right? But I also like the notion of interaction. So that's why I tend to go that way. The other one, I lose control of what's going on because I lose track of what explanation looks like. So maybe that's what we have to do at the end of the day. I'm just going to have to swallow it. But yeah.
No, the good news is you don't have to give up the notion of interaction.
Good, good. Yeah, looking forward.
But let me ask a question. You know, to me, in my experience, what we do as physicists is we look at the equations, and we decide that the free equations are the part that are linear, and the interactions are the non-linear parts. That's basically how we separate. I mean, as a working physicist.
Yeah.
And of course, there are theories in which you have just one entity. For instance, gravitation, empty vacuum gravitation, in which you have both linear and nonlinear parts. So gravity, in some sense, interacts with itself. On the same thing happens with non-abelian gauge theories. So it seems to me that our division between interacting and non-interacting aspect of nature is more of a matter of convenience, and what is tractable and what is harder to track mathematically and formally than really a fundamental aspect of nature. So I wonder if there is a true meaning or a sensible meaning that can be ascribed to something that is non-interacting.
Right.
If there is a true distinction between interacting and non-interacting things.
Yeah. Well, okay. So I mean, this is actually great because I mean, I don't mind too much the nonlinearity. I mean, I do like it. I mean, after all, I mean, that's why, I mean, it's part of yeah, no, I mean, part of the thing that I got interested in this, the Broglie's double solution theory, in which, there is it's a nonlinear deterministic equation because of similar things that you're saying, but there are other problems. So what I do think that all the issues that I personally have with the explanatory power of GRW theory has to do with the stochasticity of it. So it's not necessarily the nonlinearity of it. But yeah.
No, to me, the linearity and nonlinearity had to do with interaction versus non-interaction. That's how.
Yeah. Okay. Yeah. I mean, I need to think more about all the components.
Thank you very much.
No, thank you.
Yeah, thank you. I think Wayne wanted to have a quick follow-up, isn't it?
I don't think so. No.
No. Okay. So maybe your cat behind. He came into the picture. Yeah.
Yes, it's usually it's past lunchtime, so they're getting anxious here. Usually they get fed at noon.
Yeah. So, well, are there other questions, remarks from the people? Well, if not, let's thank our speaker again. Thank you very much for your talk, Valia, and
Thank you.
well, see you all on the 16th of May, or some of you at least on the 16th of May. Thank you very much.
Thank you.
Thank you.
Bye-bye.
Thank you very much.
Bye.
Bye.
Bye. Bye.